So, je peux y aller? Hello, everybody. So today we have the great pleasure and honor to receive Françoise Combe. Françoise Combe, I guess most people know her, but anyway, so she works at l'ALMA laboratory at Paris Observatory. She is a professor at the Collège de France, where she holds the Galaxies and Cosmology chair, and she's a member of the French Academy of Science. She has about 600 refereed publications. She has supervised a very large number of internships, theses, and postdocs. She has been awarded many prestigious prizes, so I'm not going to list them all, but I will just list the most recent ones, which are the CNRS Gold Medal, which is given by CNRS only once a year for all sciences. So it's a very prestigious prize, and the L'Oréal UNESCO Prize for Women and Science for Europe, which is an even maybe, I don't know if it's a bigger prize, but anyway, those are very important prizes. And they were awarded to her, I quote, for her outstanding contribution to astrophysics, going from the discovery of molecules in the interstellar medium of galaxies to simulations of galaxy formation with supercomputers. Her work has been essential in understanding the birth and evolution of stars and galaxies, including the role played by supermassive black holes in galactic centers. Her research is made up of observations, theoretical considerations, as well as numerical simulations, so she covers a very broad range of topics and interests. Today, she's going to tell us everything we have always wanted to know about black holes. So thank you, Françoise, for having accepted, and the microphone is all yours.
Thank you very much, Florence, for this nice introduction. So today I will speak about AGN, active galactic nuclei, and specifically about ALMA, recent ALMA results. So first, to introduce the topic, I will present this cartoon, which is about the vision that we have now for the gas around AGN. So you have here the disk. First, you have the engine, the central engine, the accretion disk, big blue bang, because it's radiating in blue, UV, and X-ray, and so on. And around, you have a gas disk that fuel the AGN. And the dust, which is in brown here, is not like we thought in the past about the dusty torus. The dusty torus was a paradigm used to explain why you have sometimes AGN of type 2, like Cipher 2, which are obscured completely. And once you are not obscured, you have AGN of type 1. And this dusty torus was supposed to absorb the accretion disk light. But here we think we have seen with mid-infrared interferometry that the dust is more in a polar direction, maybe pushed by the outflow of the AGN, and in a hollow cone, in fact. And here you have from the sublimation radius where all the dust is destroyed inside that. So the outline of my talk will be first the feeding theme that we need to transfer angular momentum of the gas, since the big problem is to exchange angular momentum. There is a lot of rotation when you arrive in the vicinity of the black hole. So for that, we need gravity torques, and I will talk about bars and spirals. I will talk then about the feedback, and we have seen with ALMA that both fueling and feedback occurs simultaneously, but in the direction which is perpendicular, jets, winds. And also I finish with this revealing molecular tori that has been done with ALMA at high resolution, at least a parsec resolution. And we discovered that a lot of molecular tori have not the same orientation as the disk orientation. So first, I just recall a few main things that we need to know to understand the following. So first, as you know, in a barred spiral galaxy, the bar is here along the x-axis, horizontal axis. it is known for a long time, for the 1980s, by Contopoulos et al., that you have orbits of stars, stellar orbits are around the bar, and then they change by 90 degrees at each resonance. So you have parallel, perpendicular, parallel, and so on. And and this is for stars because there is no collision between stars. For the gas clouds, they are dissipative, and then it's impossible that they turn by 90 degrees abruptly, but they will do that gradually like this. And you have this kind of orbit, which is precessing with a rate omega minus kappa over 2 that I will show soon in the next slides. And you have a torque from the bar to the gas because the gas and the stars are not in phase. And then you see that you will have some resonances. Here you, at the top right, you see a typical bar galaxy with a ring of gas. It is B minus V, so it's blue due to star formation in the gas. So you have a ring of gas at co-rotation, then the small one at nuclear resonance, and then in the outer parts at the outer resonance. So in fact, all these resonances are computed when you have the rotation curve of the galaxy. You have V of R, here's the radius, and here the frequencies. You can have omega, which is only V of R, V sub R. And then you can compute the epicyclic frequency, kappa, which is a derivative, second derivative of omega, and all this combination, plus or minus kappa over 2. And this curve here, omega minus kappa over 2, is exactly the precessing rate of this orbit, which are parallel or perpendicular to the bar. And this is very interesting, as we'll see later. And if you have a pattern speed like a bar at a constant omega here, you see that it crosses these curves at the resonances, the inner Lindblad resonance that we call ILR, co-rotation, and OLR. And of course, when you have these resonances, the gas is trapped there because there is no torque. It's completely in axis symmetry with the bar. So sometimes you trap the gas there and you expect that there is a secondary embedded structure, like in the simulation here. You have a primary bar, a secondary bar. In general, it's inside the resonance. You see the ring at the resonance. And you can have a secondary bar that do the same action as the primary one, but at smaller and smaller radii to feed the AGN. And to have an idea of what are the signs, the sign of the gravity torques, you can have this cartoon here, just to have it intuitively. You have a bar which is parallel to the horizontal axis. Co-rotation is there, and outside co-rotation, you have this parallel structure that get out of the bar. And the bar is dividing the plane in 4 quadrants. In fact, you can see that the tangential force that will make the gravity torque will be restoring toward the potential well, which is in the horizontal axis. And here, if you have the rotation of the galaxy in this sense, you see that the torque is positive. So all the gas outside co-rotation will go to the external resonance, OLR, while when you have the spiral structure that continues inside the bar, you have the typical dust lane inside the bar. And you see that you pass on the 2 other quadrants, the blue quadrants here. So the sign of the torque is negative now, and you understand why you are in the other quadrants. And then all the gas from co-rotation will be brought to the inner Lindblad resonance. And that's exactly what we have tried to quantify. Then you can quantify it by the observations. To have the potential, you take the old stars, you take a near-infrared image by the HST, for instance. Inside a few kiloparsec, you are dominated by baryons, so you have not to bother about the dark matter. So you take the stars, you deproject the disk, and you have the density, the Poisson equation, and the potential, and then you have the forces. So you can have all these 4 quadrants with positive gravity torques and negative, and you have to know where is the gas. And the gas is the contours of CO emission that you have here, which traces the molecular gas. And you see that most of the gas is in the blue quadrant, so negative. If you make an average in radius, you have this curve here, and this is traced by the relative loss of angular momentum. L is the angular momentum in one rotation. And you can see, you can quantify how much angular momentum you lose due to the bar. And here it's about 30%. So in 3 rotations, you will go to the center and you will fuel the AGN. So in this first step, we did that with the plateau de Bure, which is now NOEMA interferometer. And at this epoch, it was about resolution to go to 10 to 100 parsec, and about 20 galaxies. We succeed to show that only in 1/3 of cases, you have this negative torque. That is a smoking gun evidence that the AGN is fueled. And in the 2/3 of this, it's not fueled. So what happens? In fact, the gas can be trapped and stalled at resonance. Here you have a galaxy where you have a bar, you zoom in the center, you have a ring at the ILR inside the bar, and you see that the gas here in blue is trapped. And what you are waiting here is what happens here in this simulation at the top right. You have 3 snapshots of a simulation of a bar. You have indeed the gas, which is piling up at the ILR, and then progressively you have a nuclear bar, embedded bar in the big one, which sucks the gas of the ILR, and then you have another bar that can bring the gas closer to the AGN. So here you see in more detail why the gas can be stored at the ILR. So now we wanted to have more resolution to go closer and closer to the AGN to know if really these kind of torques would exist, and you can have a nuclear bar and fuel your AGN. So here, the first one we did at the cycle 0 of ALMA was this 1433. You have a big bar here in HST image with a dust lane that you see here. The spiral arms are there. And in blue, you have the HST image. In orange, you have the ALMA that the ALMA map we did with the CO322 tracer in the band 7. And what we are surprised to see is a second ring, in fact. So the gas is piling up, not in the first, but in the second ILR. And also, accessorily, we find a small, very small outflow along the minor axis, which was maybe the smaller outflow that we have seen, 100 kilometers per second. But to compute the torques, we did this procedure I just described. We just deprojected on the galaxy face-on here. We computed the torques, and you see the positive and negative quadrants. And finally, there is no gas, not very much gas in the center. And when you look at the torque, it's positive in the center. So the gas is going to the ILR in that sense. Here it's negative, so it's going from outside to the ILR. So it's piling up at this ILR, and there is no fueling of the AGN, at least at this period. In this second one, 1566, it's different, completely different. You have the big bar, spiral structure outside the bar, and what the field of view of ALMA is only 18 arc seconds. So you see that it's only a small part here. You have a ring, and the ring is at the outer parts of the fault, so it's just barely seen. And what we discovered, in fact, inside the ring, you have this nuclear disk, and with a velocity field which is rather regular. And in this nuclear disk, you have a spiral structure, a nuclear spiral structure, which, as you see, is in the same winding sense, trailing sense as the outer parts, trailing. And this was a surprise because we were expecting a leading one. And why we were expecting a leading one? And that's exactly the explanation I gave you at the beginning. We have at the periodic orbit in the stars. If now we are in the frame of rotating frame of the bar, you have parallel to the bar, you have perpendicular, and at co-rotation you have no turn because you are in the same reference frame of the bar. And of course, if there is no black hole, you have this curve, omega minus kappa over 2, which has this behavior. So when the gas loses angular momentum and dissipates energy, it is on the rising part here, and then it goes down. And we are expecting that the winding sense change. Why? In fact, I can show this little animation here. When omega minus kappa over 2 increase, you have the precessing rate, which is increasing as soon as the gas is falling in. So you see here, as a fun, you have this precessing, which is exactly going in this sense. If omega minus kappa over 2 decreases, then the orbit is going in the other sense, retrograde with respect to the sense of rotation. And you see that it is leading and trailing. So you see how this sense can change exactly. So when you are here, you are trailing the outer parts. Here you have a leading, we're expecting a leading. And then if you have a black hole, and if we enter the sphere of influence of the black hole, that you are dominated by the black hole gravity and not the bulk gravity, then all becomes a Keplerian potential. So you have this curve going up, the velocity, the omega, and every curve goes up. And then again is going up, so you are going to the trailing spiral. So the trailing spiral gives you the effect that you are entering this sphere of influence of the black hole. And here we have also make the same computation of torques, negative torque, positive torque. You see that the nuclear spiral is in the negative torque region. So indeed, this time we are fueling the black hole. And this fueling the black hole is due to the fact that it is a trailing spiral structure and you are inside this. Because if it was trailing, it would be in this side and you will have a leading and no fueling. So this kind of fueling mechanism that you have identified there is also seen in other galaxies, like for instance, 1808 that you see here. You see that you need a high resolution. Here the beam was 0.08 arcsecond, 4 parsec. And you see this beautiful in CO322 spiral structure, nuclear spiral structure inside of the ILR ring. And you see it not only in CO322, but in the dense gas tracer HCN 423, HCO plus 423. You see the rotation curve also, and we are in this kind of zone here. And of course, I emphasize that you need a high resolution because this galaxy was already observed with ALMA by Salak et al. And they saw the ILR ring, but inside they did not see any nuclear spiral structure because they had not enough resolution. So you need both. You need the large scale structure, and then you need another configuration to know what happens there, which was not seen there. Same for NGC 613. So you see here that the previous ALMA observation has seen the ring here. And in the center, there was only a disk. And here we see this spiral structure in the center. Here you see that the velocity field is almost east-west. And look at the scale here, there is 10 arcsecond. Here we make a zoom by a factor 10. Now we have 1 arcsecond. And what you see in contours is this CO322 spiral structure. And what we see in the center is a continuum. And it's also at the same scale, this HCO plus 423 that we call the molecular torus. Molecular torus because it is a little decoupled from the rest. You see the velocity field, the position angle were most east-west. Here it is north-south. You see the red and blue rotation of the HCO plus, which is the size. So we have a molecular torus inside the nuclear spiral structure, which is trailing. And of course, here you can measure the torques, same game. You have a very strong 1 in the L over L negative torque. So in one rotation, you will fuel the nucleus. It's a very good case. And now I switch to the feedback processes that we have also seen in the same galaxy 613. So you see in the PV diagram here, major axis velocity, you have a large velocity gradient that you even barely resolve. And it is on the minor axis that we can distinguish the blue wing and the red wing. And in gray here, you have the VLA jet. There is a jet, radio jet, a plasma jet, which is in this direction. And the molecular outflow is entrained by the jet. In fact, here we have measured dm over m 15 solar mass per year and a mass in the outflow of 2 million solar mass. So this is both fueling and feedback at the same time, and we need a lot of resolution to see that. In 1808, there is no outflow at the nuclear scale, so there is no AGN feedback at the moment. We have not in this PV diagram the same gradient, but this is surprising because this galaxy is a well-known outflow. You see the dust here, the dust lanes, and it is a galactic wind that is known from the starburst, but we think that it is only the feedback due to the starburst, not the AGN. And we can distinguish, thanks to the resolution of ALMA, the region where you have a diagnostic of HCN of HCS or HCN of HCO plus. We know that when you are in a XDR near the AGN, you have a large HCN respect to the other molecules, and all this in red is near the AGN, while the starburst, the further from the AGN, is blue. So you see the diagnostic tell you that you have indeed isolated the AGN from the starburst and with the resolution of ALMA. So for the feedback, you have two kinds of mechanism to have the feedback. You have first the quasar mode, radiative mode, and this is applicable essentially to the very high luminosity, high luminosity quasars when you are almost at the Eddington luminosity, so that you have a radiation pressure that pushes the gas. All the Seyferts that I will show here are more in the radio mode because they are at low Eddington ratio. You are below the 1/100th of the Eddington ratio. So there is not enough radiation pressure, but what you have is maybe the radio jet. And we think that the radio jet entrain the molecular gas. And it is the case in the prototype of Seyfert 2 and NGC 1068. We have seen this outflow. You see here the large scale CO 322 image of the galaxy with the spiral, the bar, and the ILR. And here with ALMA, you see the ILR. You see the AGN is not at the center. Frequently, you have this lopsidedness, chemical one, which is part of the fueling, in fact. The disequilibrium makes the fueling faster. And there is also an AGN, northeast, west, in this direction. And we think that the molecular torus is not aligned with the molecular torus there. It's not aligned with the main galaxy disk, which is seen at John in this cartoon. And then the outflow can sweep part of the disk. That's why there is more coupling. And you can have a larger outflow. Here is a 63 solar mass per year. And when you look in the center of the ILR, here near the AGN, you see a little disk, this molecular torus, in CO625. In CO625, you see it very short. You see it better in CO221. You are more sensitive. And also you have in CO625 the continuum around, which is the dust continuum. And the dust, you see, it's more in the polar direction. That's what we are seeing also in the mid-infrared. And I recall it in the first. And you see that it corresponds very well to the beautiful image done by Grotado et al. With FEAR, the VLT in the near-infrared. They have done that with the polarization and the difference angle with the central symmetric thing. You see here the polar hollow cone that the dust is really pushed by the AGN feedback. And you have this molecular torus that is exactly corresponding to the ALMA that we have in CO221. And you have example of this polar dust distribution. 1068, you have the polar direction in green. The dust is really in the polar direction, not in the dusty torus that we were expected from the paradigm. And it is in general due to that. In fact, you see in many cases, it is the dust in the polar direction. And I will want to show this kind of feedback here because this molecular jet is really spectacular. It is a work done with Susan Alto in NGC 1377. You have a galaxy which is almost edge-on, and you have in gray here the velocity near systemic in CO322, and only the wings in blue and red are plotted in colors, and you see that they make a jet. In fact, like a molecular jet. It's molecules, but it's molecular outflow, but it is collimated. When you have several configurations, you see it very well. It is very highly collimated, although we don't see any radio jet. That's a problem. It's the most radio quiet galaxy that we can see. Why we see it is most radio quiet? Because we see in the VLA only the core. We don't see any jet. And the ratio between radio and infrared, which is a very well-known correlation in astrophysics, is much below. This radio emission is much below the far infrared. Although it's not starburst, the radio is very, very low. And also a peculiarity is that you see that the sign of the outflow is reversing. It's blue, red, and red, blue. And this means that it is precessing. Well, in fact, the molecular jet is almost in the plane of the sky, so it's sufficient that you have 10 degrees to see this reversal in the plane of the sky. And we think that there has been a radio jet because you can only collimate if you have biomagnetic effect. Here you have an image, artist image of radio of the plasma that is in the accretion disk, the hot plasma, very well coupled to the magnetic field, which is amplified by this dynamo. And then you have these magnetic lines, which are, of course, rotating fast, and they provide this collimation. And of course, you need a plasma to be collimated, a very good coupling with the magnetic field, why the molecule outflows will not be coupled with magnetic field as much. So you need a radio jet, but we don't see it. So maybe the radio jet has gone, and we are just seeing the molecular outflow, which is still in the old geometry or morphology as it was, like it was entrained by the radio jet, but we don't see anymore on the radio jet. But we are going to do some more VLA observation, more sensitive to see if there is a weak relic of it. And here we make also a model like in the microquasar that is well known to be precessing, like by 10 degrees or so in SS433. And we think that we have about the same kind of thing. And we have modeled that. And of course, it's possible with a 10-degree precession to do that. And in this galaxy, we have seen that there is maybe both. We have seen the cone also in the molecules at low velocity. So we think that even in low luminosity galaxies, you can have the radio jets that entrain a molecular outflow, but you can also have some kind of cone. And this is due to the radiation pressure, not on the ionized gas, but on the dust itself. The dust is the location of the outflow. That's why you see the cone, the polar cone in dust. It is coming from the sublimation radius here and making this flow. Now, the third part of my talk will be about the discovery of molecular tori. So I come back to this 1C13 that I have already described, just to recall you that indeed we have a good physical observation to see that you have decoupling in orientation of this molecular torus, because here you see that the normal galaxy, at least this is a 100 parsec scale, is rotating in a different plane as the molecular torus here, which has different position angle and different velocity. So we call this molecular torus, this decoupled the molecular disk that we don't see yet because we have not enough resolution, the hole in the center, but we expect that there's a hole because like the dust is sublimated, the molecules are photodissociated and so on. But this radius should be below 1 parsec, maybe 0.1, 0.4 parsec, and we don't see it. Here I show some other example, 1326, where you see a bar here, OLR, and also a nuclear bar in colors. And what you see here, this nuclear bar, is exactly what you see in HST, this ring. It's pink because there's a lot of H alpha, a lot of new stars formed because the gas is piling in this resonance. And with ALMA is exactly what we see, the ILR here, which corresponds to this ring in HST. And inside we see this disk, which is almost edge-on here. So different orientation as the galaxy, which are almost face on. And we see this kind of nuclear molecular torus, 1365, which is a very well-known southern galaxy with a lot of the dust lane in the bar, which is a spiral inside the correlation. And you have this ring again, this ILR ring. And inside the ring here, this point here, is exactly that. So we see now something almost face-on molecular torus with a regular rotation pattern. So globally, out of the 8 galaxies that we have seen over the cycle until cycle 6, in fact, we saw that there is tori in every except this one. So the radius typically are 10, 20 parsec. They have an H2 mass of a few 10 to the 7. And the main point here is the inclination of the torus that we determine by the velocity field of the torus, the position angle and inclination. And you see the inclination is different. It's random, in fact. We expect that this gas comes from accretion at any angular momentum. And since the scale are so small, you can arrive with a polar direction or even sometimes a counter-rotating torus. And why is it misaligned? And it stay misaligned. In fact, for a while, you have a lot of instability, in fact, and a lot of instability have been already modeled and suggested by theoreticians like Pringle in 96, for instance, where he thought that, imagine that you have a warp at some point and you have an AGN, a nucleus, which is radiating a lot on the accretion disk. And if it is impinging on a surface that is almost perpendicular, then it will radiate back if it is optically thick in another direction. So it creates a torques. So we have a lot of opportunity to have torques that maintain this instability. And this was simulated by Maloney and Begelman. And you see that indeed you can maintain this warping instability and misalignment of the accretion disk for a while. You have also a lot of magnetic instabilities. And you have also this Bardeen-Peterson effect that was already a long time ago and has been revived recently in a new simulation. This is the relativistic effect of the Lens-Stirring effect that you know around the black hole. If there is a spin of the black hole, and here is the spin here, the reference frame is entrained in the rotation of the black hole spin, and it will align at the end, it will make a torque to align the gas that is infalling to the disk, and this can go up to 1 parsec. So here you have several simulations. It depends, in fact, if the disk is viscous or not, and we don't know at all what will be the parameter alpha of the viscosity. So if it is viscous enough, you will have a warp only, and if it is not viscous, you will have a break of the disk like this. So you can have several break here at different orientation according to the infalling gas. Here you see the Pounds et al. Simulation with different breaking of the disk here. And of course, if since all the radii are precessing at different rates, it's a differential precession, then all the gas rings will collide, and then you will exchange angular momentum very more quickly than you have thought with bars and so on. So you have another mechanism to fuel very fastly the central AGN. This kind of warping of the accretion disk, you see it when you have enough resolution. You have enough resolution, for instance, in when you have an H2O masers. It's the prototype of it is 4258, where you have seen this warp thing in red shifted and blue shifted. It's you have enough sensitivity because the maser is very strong, so you can make VLBI and have the resolution of this. In 1068, Gallimore et al. Have seen also this red shifted and blue shifted maser, and Martin had made this simulation here with the Bardeen-Peterson effect. And in 1068, Caproni et al. Have also made this simulation of the precessing of Lens-Stirring effect. And then it propagates until 100 parsec scale, in fact. And you can explain the for the torus that we have discovered at ALMA at 10 parsec resolution, you can explain with the simulation the time scale. The time scale of alignment is typically 10 to the 4 year. And in 10 to the 4 years, so you see it's a galactic time scale is very short. So you can imagine that there are several episodes to fuel the AGN. You have some gas that fall in, and 10 to the 4 years later, you have aligned it to the center, and you have also modified the black hole spin because at some point it should also exchange its angular momentum. So I also come back to some of this molecular theory to see if we can measure the black hole mass. If we are in the sphere of influence of the black hole, we can have, and this is the case here, for instance, you see this galaxy almost face on and the molecular torus almost edge on. You have a large velocity gradient, and we have been able to plot the velocity PV diagram here, position velocity. The observations are in color. And if you model the rotation curve without black hole, you will have this. And you need a black hole here, which is a Keplerian thing, and then you join with the bulge here to have to reproduce the rotation curve. So it was 5 × 10⁻⁷. So you see here how we can measure the black hole. In fact, for all the 8 galaxies, we are indeed in the sphere of influence of the black hole. You see the black hole contribution to the rotation curve, the bulge, and then the disk in blue. So always the black hole is dominating. You can not only in one dimension, but also in 2D, you have more information. So you can model the observations in intensity, velocity, the sigma, and measure with more accuracy the black hole. Same for 1365. Sorry, you see the model here, the observation. Yeah, this has been done also with early type galaxies. And since these galaxies have a larger black hole mass, 10⁸, less resolution was needed. This was done by the Wisdom project, Davis et al. You see how the model in blue can, without black hole, you cannot represent all the high velocity gradient, but with a black hole you can. Here again, there's an example here. And if you put all these measurement of black holes, here you are a compendium of the present state. You have the M sigma relation, very well known. And here you see the early types with a high black hole mass and the late type that we have done here when it was possible. And of course, we have a large scatter at small mass of black hole and bulge. Why? We don't know why, if it is only due to the difficulty to measure the small black hole mass, or if it is intrinsic due to the way of fueling the small black hole. So when you have more ALMA data, we'll be able to say if the scatter is intrinsic or not. Now, in the few minutes left, I will just discuss about this non-alignment that we have discovered with ALMA between the molecular torus and the disk of the galaxy. And this is not a surprise, in fact, because we knew, for instance, like 4258 with the high resolution of the maser, and also seeing the jet that is getting out. And we see here the jet in radio and in X-ray. It's exactly bent in the disk because it is sweeping up in the disk. And so this was already the signature that the molecular torus was not aligned, the accretion disk at least. And in the Milky Way also, it's a very close example. You are in an Edge-on galaxy, and you see an HCN in orange, HCN nuclear ring, and mini spiral here in green, which looks more face-on than Edge-on, so it's completely different orientation. And if I come back to the 1068, it was very hard to disentangle this orientation effect. And you see in the Manishi et al. Paper, for instance, you have this nuclear ring at the ILR. You see the scale 140 parsec. It was rotating red in the west, east, blue. When you are at the 5 parsec torus, the torus that we had discovered with ALMA, you are blue and red. So it's counter-rotating. So it's not only decoupled, it's really counter-rotating. And when you look at the H2O maser, like Gallimore, it comes back to red in the west and blue in the west. So it's only the recently accreted gas which has been accreted counter-rotating, but not, and it will be realigned with the black hole spin. And this was very hard to disentangle because we did this kind of PV diagram, and we saw velocities everywhere because it's blue, red, and then blue, and so on. So you need a lot of resolution to see that. And at the first sight, when you smooth that out, you are thinking that there is no rotation in the center and no black holes, which is not true. And when you make simulation, for instance, we did with Florent Renaud and Epsilon et al. Of Milky Way-like galaxies, for instance, and you see how this kind of gas can fall in the center. For instance, here there are snapshots of a galaxy where there was a bar, there was a ILR ring, and at some point the gas becomes unstable, forms stars. You see, you don't see anymore the ring, and then you have a feedback effect of the star formation. It goes in the halo, it makes a fountain effect, and then it comes back. And in the last snapshot, you see that it has come back in a polar structure that looks adjoined here. When you look at the face-on view, you see that the adjoined galaxy is there. The face-on view for the polar ring is indeed this spiral structure, this face-on. So it looks like this kind of thing. Of course, here it's not completely polar, but you are randomly oriented, and sometimes you can have a polar ring. Okay, so I think I will just finish it, my summary. So we have learned a lot with the high resolution of ALMA. We have learned that we can fuel by bars and embedded bars. You can have a nuclear bar and even a nuclear spiral inside. And we have learned that in the sphere of influence of the black hole, we can have a nuclear spiral which is trailing. And then it is a smoking gun evidence that you are fueling the AGN. And in the same time, in the same galaxy, you can have both the fueling and the feedback. You can have an outflow, which we can see with 300 kilometers per second sometimes, so almost the escaping velocity. And this is done for the low luminosity galaxies by radio jets, but you can have also some radiation pressure on the dust. And finally, we discovered a lot of molecular tori, which are decoupled in orientation. And we think that there are many ways to make them. We have seen precessing, because we have seen the radio jet was precessing. So this is due certainly maybe to this kind of Bardeen-Peterson effect or radiation-driven instabilities. And we can have more resolution in the future to disentangle all this. So thank you very much, and I'm ready to accept your question.
Thank you very much for this beautiful presentation, Françoise. So if those who want to ask questions, please, you go to participants and you raise your hand, and I will, and then you will have to unmute yourself to ask your question. So questions are welcome. I thought they would appear. Here comes one. Okay, Jean-Pierre Lassota.
Thank you, Françoise, for this excellent talk. I have one comment about the origin of the warp. You mentioned radiation by a Pringle model, which depends very much on efficiency of the mechanism. But and of course there's Bardeen-Peterson, but there's also a forgotten, never really developed model, which I find very promising. It is the wind-induced torque that was studied by Schandl and Meyer, my God, quarter a century ago, and was quite promising, but somehow nobody, as far as if I remember, nobody tried to develop it, because it depends more on simulation. It's not like based on basic quantities like Bardeen-Peterson and Print model, but in the context of your object, I think it is worth maybe having a look.
Mm-hmm. Yes, you're right, and it will be. We are working nowadays for another sample of 20 other objects with Sebastian Höning making some simulations of winds, and also with Kai Shiwada making some simulation of hydrodynamics with magnetic field and so on. So we have several mechanisms that we will apply to the observations to know which one is. Maybe they are playing a role all in the same time, but we are trying with observation to distinguish what is the importance of all these mechanisms.
Okay.
Brigitte Rocard?
We don't understand you.
You have to unmute your...
Unmute, Brigitte, you are muted. Yes. Oh, but we don't hear you. We don't hear you, Brigitte.
In fact, I've seen on the chat that you are asking what is the current density of the gas. So the current density, it's for 1068, it was a big question because, you know, it's Compton thick. So it's 10 to the 24. And indeed, we find evidence. Well, we have not maybe enough resolution to see all the clumps, but it is compatible with that, 10 to the 24, with the X-ray. We see the X-ray. So we think that indeed the molecular torus and also the polar, well, we don't know exactly, you have a polar cone, and at the base you have the molecular torus. So both are able to do the CFAC2 mechanism, that is to extinct the X-ray that you find in the AGN. So we are really content. And in the others, it's a little lower, but 10 to the 22, 10 to the 24. It depends on the column density, and we don't claim that we have the right one because we are not enough to disentangle all the clumps, the small clumps that could be higher column density. It's sufficient that you have less than 1 parsec clump to obscure the AGN. So we have only parsec resolution, and we don't know exactly the true.
Do you use infrared data for that too, for the
Yes,
dust or not?
In the collaboration,
Yes.
we have people doing that, and we have the mid-infrared, and also at larger scale, the Herschel, Spitzer, and so on. But at small scale, the mid-infrared interferometry. Yeah.
Yeah. So Alain Le Cavelier, please unmute your microphone.
Hello, Françoise. Thanks very much for this talk. I've seen that there are many connection similarities with protoplanetary disk physics. And I wonder if there are some connection between this community doing observation and modelization of protoplanetary disk and your community of AGN.
Yes, it's a good question. I think there was Fred Basset who was doing that. He was doing galaxies, and then he came to protoplanetary disk. But I think they use the same kind of physics, because when you have migration, you know, it is the same kind of thing. You have resonances, and you have the torques and the migration. So they copied us.
So you confirm there is connection between the two?
Yes.
People work together?
They don't work together, but they read their papers and they are inspired. But maybe you don't find frequently the same authors on the same paper, but they talk to each other.
Thank you.
But it's the same physics, it's the same equations.
Almost, it's completely, sometimes it's different. There are differences. There are analogies and differences. For protoplanetary, it's always a Keplerian potential. And you have the disk, which is not highly self-gravity. So in galaxy disk, you have in the Milky Way, you know, there is a lot of migration. The sun was not in the position. That's why you explain the metallicity of the sun, which is not the right one. It was closer to the center than it is now. So we know that the sun has migrated. And of course, in this, you have not a Keplerian potential. You have some more distributed matter, and the disk is self-gravitating. So this makes a little difference. So you have not exactly the same resonances. You have more resonances in protoplanetary disk. In galaxies, you have only 3 resonances. It's a little different, but some mechanisms are the same.
Pierre Guillard?
Hi, Françoise. Hi, everyone. Thanks a lot for those this beautiful summary of observations that are very rich. So you've touched upon the difficult issue of the AGN efficiency to launch outflows, and as you well know, for a given AGN luminosity, there's a huge scatter in the outflow rate of mass that are launched, and I was wondering about your view at this diversity, and do you think the connection between the dust obscure torus and the circumnuclear matter, is it the key to understand this diversity? Do you think this counter rotations or this decoupling between the torus and the circumnuclear disk, is it the key to understand this problem?
Yes, I think it's a key, because people were selling. Sometimes there was a polemic discussion between some people say, well, the jets, for instance, if it is a jet, it is perpendicular to the disk. So once you have emptied the collimation zone, you don't couple to the galaxy and you don't make any feedback. But in fact, it's not like that. The jet is perpendicular to the accretion disk and molecular torus, which is randomly oriented. So you can at some time sweep the galactic plane and sometimes another region. So it's never the same region. So even if you have emptied one region, you have another gas to empty. So you have always some gas to feedback and couple. So you have more efficiency of feedback if you have this randomly oriented, and you don't know, of course, the duty cycle of this. This is a question that is very debated. People think that it is a million years or 3 million years.
Yeah, that was my next question.
Then it is really, we are battling inside the same paper or the quarter of the same paper. Some are telling, well, when you see the radio jets, you have giant radio jets, they are going to 1 megaparsec, even more. So you're telling that in one episode. So in one episode, the lifetime of the AGN is 10 to the 7 years. But when you look at the narrow line region, sometimes it is limited, 1 or 10 kiloparsec, no more. So you say, well, maybe it's 10 to the 4 years, but not because you are matter bounded, maybe. So you have not enough gas in this direction. So maybe the ionizing photons of the AGN are escaping. Or if there is enough gas, you are radiation bounded, like a Strongram sphere, if you want. So it's very small, but it is because of the recombination and so on. So you have an equilibrium. So it can be 10 to the 6th year, the duty cycle, but you see a small narrow line region and so on. So this is still debated, and we have to work more on this topic.
Okay, thanks very much, Françoise.
Any more questions? Patrick?
Hi. Yes, I have a question about the filling factor or the covering factor of this gas, because what you show, okay, it seems that there is dust everywhere, right? So not only in a disk or in a torus. Mm-hmm. So the question obviously is, maybe you cannot answer from observation because you may not have the resolution, but at least from simulation. So what is the...
Yes, we think that the filling factor is very small. There are clumps everywhere. In the simulation, of course, it depends on the physics you put in your simulation. If you put the H2 formation, how much radiative transfer you have. But the clumps of molecular clumps are very small. And they're very dense, but very small. So we don't know exactly if they are 0.1 parsec, 0.2 parsec. We know in the Milky Way that you have a fractal structure, and from 10 to minus 3 parsec to 100 parsec, you see all this kind of molecular clouds. So why not in the AGN and near the center? So you can imagine that you can have many clumps below the 1 parsec scale. And then we have not enough resolution for the AGN to tell you.
What kind of resolution would we need?
We will need 0.1 parsec, because we think that the sublimation radius, at least the whole of the molecular torus, should be 0.1 parsec or so, maybe 0.2. But for the moment, we have the largest baseline with we have 0.02, 0.03 arcsecond with ALMA. And even here, we are a little bit limited by the resolution of the sensitivity. Then we can think of VLBI, but then VLBI, you need something very strong, like radio jets. We see the radio jets, we see the image of the black hole with the plasma rotating. But for the molecular torus, it's not so strong. So
you don't have the sensitivity.
We have not the sensitivity. So with SKA that we were discussing previous with the students, that with SKA we could, if we have a high resolution, we could have some molecules with 0.1 parsec in the SK2, the second part of the SKA. So because then there will be the surface and the sensitivity to see that. Maybe.
Oh, so there's hope.
Oh, yes, yes.
Raphaël Duquet?
Yes, just one question. I was wondering, on a larger scale, what were the influences of inflows from the circumgalactic medium, for example, either on the precession of the jet or on the warping effects that you talked about earlier?
You mean the influence of the inflow of gas?
Yeah, the inflow of gas on larger scales from the circumgalactic medium.
Yes, in fact, so you have always gas inflowing and making reservoir for this fueling. But then, of course, if the jet and the molecular outflow is impinging on the disk, then you have some shocks. And it is seen in 4258, for instance, you see the shocks, you see the jet is changed, and Centauri also you see that. So you can have also a jet-induced star formation, because when you have a shock, you have star formation, you trigger the collapse of clouds. So you have a secondary positive feedback. Sometimes it's negative, sometimes it's positive. It's not a very strong phenomenon, but it is observed.
Thanks.
Well, are there any more questions?
Florence?
Yes, Pierre?
Yeah, wonderful talk, Françoise, and I got very inspired. I was wondering if you had any sort of comments about what you have learned from the, let's say, local universe that could be applied to the early universe at high redshift, looking at the same phenomenon of feeding and feedback.
Yes, so you're interested in your program at high redshift outflows.
No, not at all.
So I think that this kind of things, of course, it's less violent, but in nowadays galaxies, it's calm and stable and so on. So galaxies in the high redshift universe are more violent, they're more unstable, there are more gas. So, but there is also bars. We see bars and spiral. So you have a lot of possibilities to have non-axisymmetric feature, to have torques, and to have a fueling of AGN. So we need to fuel AGN very quickly because we see a 10 to the 9 solar mass black hole in the beginning. I think you have the possibility to fuel without stopping, because in Z equals 0, you have some gas falling in and then you stop. You have a duty cycle, which is full of holes. But in the early universe, you will have Eddington luminosity for a long time. So you can grow the black hole much more efficiently than today. But the mechanism could be the same, except that there is some more interactions. So the tidal torques could be more important than maybe the internal and secular torques like the bars, because there are more interaction.
Interesting. I think it will be quite interesting also to look at the cases that are gravitationally amplified, so that you can really look at the
with the lenses
that are commensurable with what you see in the local universe.
Mm-hmm. Yes. Mm-hmm.
Nice prospect.
Lots of nice prospects. Okay, well, if there are no more questions, then I think we can stop here and thank Françoise again for this very nice talk, and wishing you good luck for your large program with ALMA.
Yeah, thank you very much. Bye-bye.